off of that line there?
So the
or the
tropomyosin,
tropo complex, I mean.
So what happens is underneath this line, there's little dents. So whenever it's time to contract, they're going to shift upwards, and those dents will be grabbed on by the myosin. So
Okay.
it'll have little handholds.
Hmm.
Myosin, look at him and his little hands, so grabby. So with myosin, they're going to make up your thick myofilaments, and they're going to extend the entire length of the A band. Okay, so they don't happen in the I band. Now they're going to have these little projecting heads called cross bridges. So depending on your book, some books will say those are projecting heads, and they're only called cross bridges when they grab actin. I'm not that nitpicky. It's kind of like, these are my hands. If they're not grabbing their hands, if they are grabbing their hands, their hands. Okay. So you can call it a cross bridge. You can call it a projecting head. I use them interchangeably. But some of the books, if you read them, or some of the articles, they'll have projecting heads, and they'll say cross bridges only when they grab actin. So those are the little parts that reach out and pull actin so we can have a muscle contraction. Not only is myosin going to fuel contraction by grabbing and pulling onto actin, it also is going to be able to break down energy to fuel the grabbing. So it's the grabber and the energy for the grabber. So myosin will act as ATPase, adenine triphosphatase. They're going to be the enzyme to break down ATP. And of course, anytime you put ACE at the end of the word, that's just the enzyme that breaks down that word. So it's going to break down ATP so it can grab, break down ATP so it can let go, break down ATP so it can grab, break down ATP so it can let go. So it fuels as well as does the contracting, the grabbing. Okay. And here's just showing you everybody together. So in the H zone, that's sometimes called the bear zone, it doesn't have any of those cross bridges. It doesn't have any of those projecting heads because there's no actin to grab. So what's the point of having grabby things if you can't grab anything? So that part of the myosin doesn't have any of those projecting heads. Here in the zone of overlap where actin and myosin are both present, they're going to have the little heads so they can grab on. And of course, actin is there to be grabbed. And as long as tropomyosin is covering up those binding sites, you can't grab onto it. Just like if somebody's blocking the handhold, you can't grab onto it. Same thing, they just kind of different artists, but here's our actin. And in this picture, they colored the active sites yellow. Okay, and so instead of making them a dent, they just made them a different color. So that tropomyosin is sitting on the yellow, sitting on the active sites, and troponin is attached to the tropomyosin. And as long as we have these guys in place, nobody can grab actin because they're covered up. Now, we don't care about the other proteins. So if you're thinking, wow, how many of these little proteins do we have to know? At least you don't have to know nebulin or G-actin or F-actin or actinin or titin or any of the other stuff. Okay, so we're just caring about actin, tropomyosin, troponin, and then on the thick filaments, just myosin in its little hand so it can grab onto stuff. Any questions? So that's the anatomy. That's the parts. Okay, so we're about halfway there. And of course, that's what we've been talking about in lab, the different parts of the muscle cell models. Now we've got to make them work for us. Now we need to do the physiology. Now, when we look at muscle contraction, when you move, when your muscles contract, we have three different processes that get us to the point of contraction, three different steps to get there. The first step is excitation. Excitation is when your neuron tells you to contract. Okay, it's time, go contract. Then we have excitation, contraction, coupling. This is everything from the point the neuron tells the muscle to contract and the muscle cell is actually contracting. So there's several steps to prepare the muscle cell to work, to prepare the muscle cell to contract. And then we have contraction proper. So when we're actually, myosin is grabbing onto actin and we're contracting the muscle cell. Okay. So it's kind of like if you're at home, how do you know it's time to eat dinner?
When your stomach rumbles?
Yeah. Oh, you're one of those people that have a time. I heard time over there. I'm not that organized at all. There are those people who's like, it's 6:15. I am 15 minutes late making dinner. I'm the person that rolls in going, what is going to talk to me today?
Mm-hmm.
So I know when it's time to make dinner when my kids go, hey, I'm hungry. I'm like, all right, I guess I'll make dinner. And no need to make it if no one's hungry. If no one's hungry, I'm just going to sit here and pretend I don't exist and maybe I won't have to make dinner. Sometimes you have those moments. Okay. So your kids say, I'm hungry. That's how you know it's time to make dinner. That's like excitation. The neuron says, hey, you need to contract. Now, when it's dinner and your kid says, I'm hungry, between I'm hungry and the kid's eating, what happens?
Your stomach growls.
Well, there's that. But between the I'm hungry and we're eating, what has to happen?
You're cooking it.
You got to make dinner, right? And depends on how fancy your dinner is. It might be simple as open up a can of SpaghettiOs, put it in the bowl, and put it in the microwave. Bon appetito. Or you got to go real fancy with it. Okay, so there's a lot of steps between I'm hungry and I'm eating. That's excitation, contraction, coupling. That's where the bulk of the processing is occurring. We're going from the being told to contract to actually contracting. And then contraction. Once dinner is on the plate, you are going to eat dinner, right? And if you're having one of those bad days and they're like, but I don't want to eat this. Like, well, you should have said something while I was cooking it. It's on the plate. You're going to eat it now. Ever have those moments?
Mm-hmm.
And then, you're like, I'm going to be a strong parent. You eat that or you go to bed hungry. An hour later, like, here's your granola bar. I kind of feel guilty. Okay? But once it's on the plate, you got to eat it. Once we've gone to this point, we will have muscle contraction. There's no stopping it. Even after you're dead, your muscle will still contract if it gets to that point. That's why we have things like rigor mortis and twitching after you die. It's because it's got to grab. It can't say no if the conditions are right. Got to eat the dinner if the dinner is on the plate. Yes, ma'am?
Would this also relate to like the reckless leg? Like,
With that one, you most likely have nerve misfirings. So that'd be like your kid was telling you they're hungry all the time. So you're always making dinner, always cooking, even though you're not really hungry. So that one, they have to tell your kids to shut up. So they have to tell your nerves to stop firing. So, nerve supply. As we learned, skeletal muscle is voluntary. It cannot contract without the nervous tissue telling it to do so. So if you sever connection between the brain and spinal cord to the muscle's dead in the water. So the neuron that tells your muscles when to contract is called the somatic motor neuron. Now, when we get to the nervous system was developed, or studying of the nervous system was developed by a lot of people who were really proud about their jobs, right? We all know neurosurgeons are very uppity, like, I'm a neurosurgeon. You're like, wow, good job, right? They're kind of, I'm here, you're here kind of people. In order to make sure everybody knows how great the nervous system is and how important their jobs are, they have a lot of terms that they use to make themselves sound more important. Okay, so half of learning nervous tissue is just decoding what these people are saying because they got to use big words to describe them. So somatic motor neuron sounds fancy. Okay, somatic, that means body. Motor, what does motor mean? Movement, right? If you got a motor, you can move, and a neuron is a neuron. So a somatic motor neuron is a neuron that moves your body. So it sounds fancy, but he's just the one that says move. I'm hungry. So that is the neuron, the nerve, that is conducting the impulse to the skeletal muscle. So in this image, we've got two motor neurons. We've got the blue one going to the blue muscles and the red one going to the reddish-pink muscles. Now, a motor unit's like an army unit, right? The army unit has the commanding officer and the people he controls, right? They follow orders. That's what a motor unit is. You've got your commanding officer, the somatic motor neuron, and all the muscle cells he controls. So anytime the motor neuron says jump, these muscles twitch. They're going to jump. They're going to contract like they're supposed to do. Now, motor units are different sizes, just like they are in the Army or any military branch, right? Whenever they had to go and find Osama bin Laden, I have to say it slow because I always want to call them Obama and Biden, but apparently those are the good people. Mess with my heads. But when they went off to go kill or capture Osama bin Laden, did they send a huge military force into Afghanistan to do that?
yes. No.
No. Has it been so long since we've killed those guys? So when you want to do something pinpoint, precise, precision, you send a bunch? No, right? How many you send? Big numbers, little numbers? Little numbers. When they took out Osama bin Laden, they sent, SEAL team six. 6 guys went in, handled business. Okay. If the whole army would have shown up, he would have been like, "Look, there's a bunch of dudes on this, horizon. I'm going to go hide in my hole." That's how he got away for so many years, because he hid. Here, we're very precise, very pinpoint. Now, if you were going to invade Africa, would you take 6 guys to invade Africa? No, the lions would get them. You got to have a really big army to do something big. That's how the body works. If we're going to do something precise, you're going to thread a needle. You're going to write your name in cursive using your pencil. You're going to put some beads on a necklace. That's very precise. You're going to use very small motor units to do that. If you're standing, if you're kicking a soccer ball, you're going to have very big motor units, right? If you're going to go do leg presses at the gym, you can't do leg presses using just your hands. That would hurt. Okay, so we have big motor units that can give us strong, that can give us powerful, but they can't do precision. Okay, and then we have small motor units that are very good at precision, but they're not good at power. Okay, and again, this is stuff you can check out at home, right? You can't go and try to do powerlifting with just your fingers. That's going to break something. You can't write cursive with your knees. That sounds like a fun party game, right? Put a pin there and try to write your name. Not going to work out right. It's going to look weird because your thighs have huge motor units. They're built for power and strength. They're not built for precision. You can't thread a needle with your knees or anything like that. So your big motor units are going to be strong and powerful. Your little motor units are going to be more precise, more delicate movements. Our motor end plate. So as we've talked about in lab, you've got an entire muscle cell and the membrane, the sarcolemma. When a neuron talks to a muscle cell, he doesn't talk to the entire muscle cell. Because if that muscle cell is 12 inches long, there's no way that neuron can talk to all 12 inches of that cell. It goes to one spot. It goes to the motor end plate, and that's where it's going to tell it to contract, right? Whenever your kids are telling you they're hungry, do they talk to your feet? No, right? Unless your kids are weird, right? When they tell you they're hungry, where do they talk to? Your face, your ears, where you hear things at. They don't mumble at your ankles. Okay, they're going to go to where you need to, right? When you park your car at home, you don't park anywhere on your property. You park on the driveway that's made to have your car. That's that motor end plate. It's the part of the sarcolemma that is made to receive neurotransmitters. So it has a special look to it. It has all those extra wrinkles, those subneural clefts or junctional folds to absorb and bring in the neurotransmitters. So the area of the muscle sarcolemma adjacent to the synaptic end bulb. Neuromuscular junction, as the name suggests, this is where a neuron and a muscle hook up. Okay, so you have the axon terminal branch synaptic end bulb of that somatic motor neuron. You've got the motor end plate associated with that muscle cell, and that's when we're going to release our neurotransmitters and receive those neurotransmitters. That's going to be that neuromuscular junction. Oh, look at that. It's kind of like something we've seen somewhere before in lab, right? Maybe on 2 of 3 models. Okay, so here's that axon terminal branch, the synaptic end bulb, kind of bulby shaped. There's our muscle. And of course, that one wrinkly area we're parked at, that's that motor end plate. And we release neurotransmitters, and it's going to float across the synaptic cleft to be picked up at the subneural cleft or the junctional fold where those receptors are. So those receptors, notice they're only found here. They're not found all over the place. This is a slide showing you here's a somatic motor neuron communicating with several different muscles. So you have that neuromuscular junction, that hookup, so they can talk to each other. So we're going to start with the I'm hungry. We're going to start with excitation, the neuron telling the muscle it's time to contract. So we get that nerve stimulus. So we're going to have a nerve impulse, action potential, travel down the axon terminal branch to the very end of that axon, the synaptic end bulb, the end that's bulb shaped. Once that stimulus gets down there, it's going to open up calcium channels and allow calcium to come in. So there's calcium all over the place. So we're just going to let it come in. Now, once calcium is in the cell, it's going to kickstart a little chemical reaction. We're not going to concern ourselves with this chemical reaction because that's just too much. That's another page of notes, and we don't want to have to deal with that. But just know that that calcium causes the synaptic vesicles, the little bubbles that hold neurotransmitters, to float to the surface of the cell. And when they get to the surface of the cell, those synaptic vesicles are going to release their neurotransmitter. In the case of the somatic motor neurons, that is acetylcholine. So acetylcholine is one of the most important neurotransmitters that we have in the human body. It's in the top two, which is code for, we're going to be talking about acetylcholine for the rest of the semester. And then into A&P2, you're going to be talking about acetylcholine because this is the same guy that slows your heart rate down and tells your muscles when to contract so you can have high blood pressure, low blood pressure, stuff like that. So it's going to be something that we're going to see throughout A&P1 and A&P2. So acetylcholine, and it's nicknamed the ACH. Okay. So we're going to release acetylcholine into the synaptic cleft, the space, and it's going to float across that space until it gets to the subneural cleft or junctional fold, and it's picked up at the receptors. Okay. Now, those receptors are called ligand-gated channels. We don't care, but it's something that your book always utilizes. It's a special type of door into the muscle cell. It works like a key in a lock. Okay, so when you turn a key, it unlocks a lock, right? That's kind of a thing. So what acetylcholine does, it is the key, and it fits into a special lock, that receptor, and it's going to open the door. Okay, so that is excitation. That is the I'm hungry, just like when your kid says I'm hungry travels across the air, goes into your ear hole, and you process the words I'm hungry. So here it is in picture form. So we have that action potential coming down. That allows calcium in. That causes the synaptic vesicles filled with acetylcholine to float to the surface where they pop, raining down acetylcholine, just like opening up a bottle of Coke allows the bubbles to come up to the surface and pop and release. The acetylcholine will bind to the receptors, and that's going to open up a sodium channel. So just like a key in a lock is going to open that door, and that's going to allow sodium to come in. We're not going to detail what sodium and potassium are doing because that's going to be test 4. Okay, so we'll be talking about neural transmission, sodium, potassium on test 4. If we covered that today, we'd all start crying more than we're already thinking about doing right now. Okay? So once we've turned on that cell now knows it's time to contract. We're going to break down excessive neurotransmitters so we can stop stimulating that muscle cell. We don't want to overstimulate. And that resets us back to normal. And we can do it again. Same thing, different artist. So this one does show you the calcium coming in. That calcium is going to make the synaptic vesicles go to the surface and rupture, releasing acetylcholine. You can find pictures of this online, electron microscope pictures. When the channels release the acetylcholine, it looks like someone just turned on a shower head and it's raining down. So it floods the synaptic cleft with acetylcholine. And that acetylcholine floats across the synaptic cleft, binding to that receptor. So this would be that ligand-gated channel. And that's going to open it up so sodium can come in and potassium can go out. And so that's excitation. We just told the muscle it's time to contract. So now we've got to prepare and enable contraction. So that is the excitation-contraction coupling between I'm hungry and I'm eating dinner, between the excitation and the contraction. We got to do the middle stuff, the coupling. So that nerve impulse that stimulated the muscle cell, that's going to cause an action potential to travel along the surface of the sarcolemma of the cell membrane. And of course, we've got those T-tubules, those doorways in. So that urge to contract will come into the T-tubule, and being a part of the triad, on either side of the T-tubule, we've got a sarcoplasmic reticulum, right? 2 sarcoplasmic reticulum, 1 T-tubule giving us a triad. So the urge to contract comes into the T-tubule, goes to the sarcoplasmic reticulum and says, let it rain, okay? We're going to release lots of calcium because we've been storing calcium for funsies. And this calcium is going to rain down in the sarcoplasm, in the cytoplasm of the muscle cell. And this calcium does 2 things. One, it is going to remove the troponin-tropomyosin complex from the active sites of actin. I know, big words. So calcium will bind to troponin. When it binds to troponin, it's going to twist and change the shape of troponin. In chemistry land, it's called changing conformation, okay, because it changes shape once it attaches. Now, since troponin is attached to tropomyosin, if we move troponin, tropomyosin has to follow. So that's going to move troponin, move tropomyosin away from the binding sites so it can be grabbed upon. That calcium is also going to go to myosin and go, guess what, boy, let's break down some ATP. We're about to grab ourselves some actin, son. And it allows us to break down ATP so myosin can grab. So it's going to make it available for grabbing and allow myosin to have the energy to grab. Yes.
So is calcium the handle, so to speak?
It's more of a trigger to kickstart things.
Okay.
So here we have it. That action potential, that excitation traveling down the sarcolemma comes in at the T-tubule, stimulating the sarcoplasmic reticulum on either side, allowing that calcium to rain down. And when it rains down, it will bind to troponin, twisting and changing the shape of troponin. And since troponin is bound to tropomyosin, tropomyosin also has to move with it, opening up those active sites. Now we've got little handholds that the myosin can grab onto. And so dinner's now on the plate. The only thing left to do is to eat. Okay. And at this point, there's no stopping it, right? Once dinner's on your plate, you will eat that for dinner. Once these active sites are available, myosin will grab it. And this is why we have rigor mortis and muscle contractions after death. You get to this point, it don't matter if you've been dead for hours, we're still going to grab it, and we're still going to contract. Okay. So muscle contraction. And again, a lot of times this is referred to as the sliding filament theory because myosin and actin will start sliding past each other. So the filaments are sliding filament theory. So we have myosin. It's going to break down ATP to release the energy. That gives it the energy to grab onto that active site in actin, and it's going to pull. It's going to break down ATP to let go. Then it's going to break down ATP to grab and pull. It's going to break down ATP to let go. It's going to break down ATP to grab and pull, break it down to let go, and it's just going to keep traveling further and further, jumping from binding site to binding site to binding site as we crawl up the actin. Okay? Just like when you pull on a knotted rope when you play tug of war. We've all played tug of war and have seen tug of war. Right? So we energy to pull, energy to let go, energy to pull, energy to let go, over and over. Now again, those actins are attached to the Z lines or the Z discs, right? That's their anchor point. So they can't unravel. So as myosin is grabbing that actin and pulling, it's pulling to the center. It's pulling towards the middle of the H zone. So as it's pulling the actin is going to get shorter and shorter. The Z lines are going to get closer and closer together. As we get the Z lines closer and closer together, that's going to make the I band get smaller. It's going to make the H zone start to disappear. And we're just going to keep pulling until the Z lines come in contact. Once we touch, we can't get any closer than touching, right? Right. You can't be like, now I'm going to get closer. It's like, dude, you're already touching. Stop it. Right? So once they come in contact, you're done with the contraction. When you tug a war, once the flag on the rope is across the line in the sand, you're done. You don't have to keep tugging anymore. Okay? Now, this is happening in this sarcomere, but it's also happening in all the adjacent sarcomeres. So all the sarcomeres are getting shorter and shorter and shorter until they touch. That makes the whole myofibril get shorter and shorter. And you get enough myofibrils getting shorter and shorter, the entire muscle gets shorter and shorter, muscle cell. And then the whole muscle cells working together, the fascicles are going to get shorter. And if enough fascicles get short enough, the muscle organ gets short enough, and it causes contraction. Okay. So here's our guy at rest. Our active sites are covered up by the tropomyosin. Once we expose them, myosin got to grab him some actin. So we're going to break down ATP to grab and yank. ATP to let go, ATP to grab and yank, APT to let go, over and over. We're just going to keep pulling and traveling down these active sites until we get to the end. So the Z lines are getting closer and closer. The I bands start to disappear. The H zone starts to disappear. And once the Z lines touch each other, we're done because we can't get any closer to touching. Make sense? It's great. Let's do it. All right. Crappy picture time because we love crappy pictures. I'm convinced that you said, yeah, we do. All right. So if we look at the whole process, we have our synaptic end bulb, and it's got little synaptic vesicles filled with acetylcholine. We've got our muscle cell. So we've got the motor end plate with our subneural clefts or junctional folds, all foldy looking. And as we travel down the sarcolemma, we've got our T-tubules. And on either side of the T-tubule, we have the sarcoplasmic reticulum along the entire length. Inside, we've got our actin. And at rest, we have tropomyosin covering the binding sites and our troponin attached to it. And myosin is just sitting around doing nothing because it can't do anything, right? So when we go through step by step, we start with excitation. Action potential travels down, and it's going to open up calcium channels to allow calcium to come in. Now, calcium is going to kickstart a reaction that will cause the acetylcholine to rise to the surface, releasing the acetylcholine. And it's going to float across the space until it binds to the receptors. That's going to send an action potential. So far that has been excitation from this point to this point. Then we've got excitation contraction coupling. The impulse travels down the sarcolemma and comes in at every single T-tubule. And of course, the T-tubules are flanked by sarcoplasmic reticulum. So when that urge to contract comes in, it's going to tell the sarcoplasmic reticulum to release the calcium. Make it rain. So calcium for everybody. Oh, so much calcium. Got to get a hand cramp. Writing calcium. Now that calcium is going to float down and it's going to bind to troponin. And when it binds to troponin, it's going to twist, changing its shape, which will then cause tropomyosin to move out of the way. Okay? And I'm just going to draw a really big active molecule. Oh, there's a Z line. The end. Okay. That's excited. Myosin, go grab himself some actin. Break down ATP, grab, yank. Break down ATP to let go. Break down ATP to grab and yank. Break down ATP to let go. Break down ATP to grab and yank. Break down ATP to let go. Break down ATP to grab and yank. Break it down to let go. I know, it gets crappier as we keep drawing them, so just gonna happen. Grab, yank, let go. Wow, I don't know what happened with that piece of myosin. And then we're done. No more grabbing and yanking because we've reached the end. So we pulled and pulled and pulled and pulled and pulled that active until there's no more pulling capacity because we've reached the end, we've reached that Z line. So that's your contraction. Okay. Now there's lots of resources for this. So again, that's like the only good thing about having an e-textbook. There are videos. So you can have videos for excitation and it'll take you through step by step. There's videos for excitation contraction coupling. There's videos for the muscle contraction, sliding filament theory. If you don't want to use your ebook, you can go onto YouTube. A lot of the publishers' videos have been pirated and put on YouTube, but you do have to put in muscle excitation. If you just put in excitation, I cannot guarantee what you were going to be viewing is safe for your viewing eyeballs. Okay? Stuff be popping up on YouTube. But you can go to the specific YouTube University or YouTube U should just be educational videos instead of just random gamers or whatever they have on YouTube. Okay, so you can Google these, you can find these videos all over the place. So if you want to have the different views, different versions, you can do that. Now, if we want to use analogy, because sometimes we love us some lame analogies, right? I'll pretend you said yes. I'm going to keep going. Okay, so for our lame analogy, we're going to have a party because why not, right? Yeah, we deserve it. So let's have an ice cream party. Okay, so why do you think I chose ice cream party?
Because we all scream for ice cream.
We're all screaming anyway. But yeah, that's good. But specifically, what up there would make you think
The
ice cream?
scoop. No.
What's one of our big players up there?
The calcium.
Calcium.
Oh, because that's
Ice
ice cream's
cream
made of
made
calcium.
of milk that has calcium.
Mhm.
That's the reason why it's not a pizza party. Though pizza has cheese, you could work it.
Okay.
Ice cream sounds more fun. Okay. So we're gonna get ice cream from an ice cream factory. We all know that in order to make ice cream, the ice cream factory has to have milk, right?
Mm-hmm.
So that's this up here. Now, we probably don't know what's going on within that ice cream factory. And I'm sure many people don't know. That's why occasionally ice cream factories keep trying to kill people, right?
What?
There's a Blue Bell, Blue Bunny, one of the blue ice cream people. They're like, and now we got the E. coli again. Don't eat our ice cream. Awkward. All right. So ice cream, in order to make it, you got to have milk, but magic happens. So we don't care about that. So we're going to have the ice cream factory. Let's call it Haagen-Dazs, because if you're going to pay that much for ice cream, they better home deliver, right? That's expensive stuff. So calcium comes in, and once we have calcium in, we can make the ice cream. So we're going to have our delivery guy leave the ice cream factory, and he's going to drive to your house. And when the delivery people get to your house, what do?
Ring the bell.
They ring the doorbell, right? And when you ring a doorbell, it sets off an electrical impulse to the bell so it has a chime. Okay? We don't care how it works. That's going to be test 4 when we care about electricity. Okay? But not today. Not today, Sadie. Okay, so once we've rang the bell, someone's got to come answer the door. So it's T2 doorways into the cell. If you're at a party, let's call it a kid's ice cream party, who usually has to answer the door at a kid's birthday party?
Parents.
Parents, right? Here comes mom answering the door. So now we've got the ice cream, and her job, distribute. Okay, ice cream for everybody. Calcium floods the system. Then you got this couple. We've all seen them, right? This is the clingy girlfriend. This is the guy without a spine, right? Yes, ma'am. No, ma'am. Let me carry your purse. You look pretty today. Yeah, that guy. Okay, and then her that controls him. Okay, so she sees ice cream. And she's like, "Look, honey, there's ice cream." And he's like, "All right." Okay, because when you've got a good seat at a party, you don't want to get up, because what happens when you get up from a good seat at a party? Yeah, somebody else get your seat. So he's like, yeah, that's nice. So she sees that ice cream. She's going to change her shape. Look, honey, ice cream too. Get your ass up. We are getting us ice cream. Yes, ma'am. Change shape, pulls him out of the way. Okay. Once that is available, someone will slip in. There's myosin. Slipping in. Coming into that seat. Okay. Now that might not be the best seat in the house, so we're going to spend energy to get up, walk to the next seat. Oh, I don't like this seat either. I'm going to spend energy to walk to the next seat. Don't like that one either. And we're just going to keep moving seats until we get the best one closest to the TV so we can see everything. Okay. So that's what myosin is doing. He just keeps spending energy, walking down, getting into each of these active sites until he can get to the end, the best one. And by then, muscle contraction's done. We're at the best one. Okay. So excitation, contraction, coupling, and then the contraction itself. Again, it may take a few drive-bys, a couple of readings, some prayers, crying. It'll get there. When we have low intracellular calcium, all that calcium is stored, not floating around in the cytoplasm. The tropomyosin is going to block the binding sites. Myosin isn't going to grab actin. The muscle stays relaxed. So as long as calcium is locked up, we will not have muscle contraction. When we have high intracellular calcium, that calcium binds to troponin, twisting, changing the shape of troponin, moving tropomyosin away from the binding sites. Now the site is active and myosin can grab onto it. We will have a contraction, that sliding filament theory. Cross-bridge detachment also requires ATP, right? Takes energy to sit down, takes energy to stand back up. Okay, so anytime we grab and yank, anytime we let go, it's going to require energy to do that. Now, the binding of acetylcholine will open sodium channels, causing a little action potential. That's you push the button for the doorbell and a little electrical current goes and makes the bell chime. We're not going to detail the doorbell functioning at today's party. We'll save that for next week whenever we get to test 4 material. So our triggers for contraction. The initial trigger is neurotransmitter binding. So once this happens, the muscle is going to start preparing to contract. Okay? Just like once your kid says, I'm hungry, and it hits your ears, you're going to start thinking about dinner, start making dinner, start doing something. Our final trigger is calcium binding to troponin. Once this happens, it will change shape. That will move tropomyosin. Myosin will sit down in the binding site. Once dinner's on the plate, you will eat dinner. There is no stopping it. Okay? So if you're in the middle of cooking and someone calls and says, hey, I've got pizza, you're like, I haven't gone too far yet. I'll just stop and we'll do this tomorrow and we'll eat pizza now. But once dinner is like, dude, I can't come eat dinner with you. I'm already eating dinner. Too late. Okay? Now, these 2 trigger points are crucial for medical use. Some medications stop the initial trigger. So that restless leg syndrome, if somebody has that condition, they can take a pill that blocks neurotransmitter binding and the muscle won't contract because it never is told to contract. So some of our muscle relaxants do that. Okay, they stop the initial. Some of our stuff blocks the final. We don't see this as much in skeletal, but if you've had heart arrhythmias or you have high blood pressure, they can put you on calcium channel blockers. Calcium channel blockers will slow your heart rate because it prevents this binding. And calcium channel blockers will slow and lessen your smooth muscle contraction, lowering blood pressure. Okay, so we can hit the final trigger, or we can hit the initial when we want to do regulation. So a lot of your medications hit one of those 2 spots. Your medications don't hit any of this, because what's the point? Okay, once this has happened, you're not going to have any medication that can stop this part from happening. It's going to work. So we're going to tag here, we're going to tag there when it comes to medical treatments. So in case you wonder, oh, how come calcium channel blockers can help your heart and lower your blood pressure? Takes out calcium, which is that initial trigger, that final trigger for muscle contraction for all muscle, smooth or heart or skeletal muscle. And of course, you'll learn a little bit more about that in A&P2 when you get to the heart muscle and you get to the smooth muscles and such. So there's the initial neurotransmitter binding. Now we know the kids are hungry. We're going to start making dinner. Once we have that neurotransmitter binding, we're going to start excitation, contraction, coupling. And that final trigger, calcium binding to troponin, there's no stopping it after that point. You will have muscle contraction. That's why you end up with rigor mortis or twitching after death. It causes this issue and it allows you to continue the contraction force. So once dinner's on the plate, you are going to eat that for dinner. There's no stopping. That was the big hump. Now we're going to go to a little hump and then it'll go downhill. Woo. So muscle metabolism. In order to contract, in order to have myosin grab and let go, we've got to have ATP to fuel that activity. So our muscles are going to have to make and generate and utilize ATP. So let me erase this mess so I can draw a brand new mess. Yay, new messes. For Ginger Care. Thanks. All right. So when we break down ATP, again, we're going to have ATP. You have to have the enzyme ATPase. Got to have some water. It's a hydraulic reaction. And you're going to end up with ADP, adenine diphosphate, plus a phosphate, plus energy. Now, all cells can do that. Okay? Every single cell in the human body does that to run their activities. Now, when we look at muscle cell, we generate ATP to utilize, and we try to stockpile it, but unfortunately, ATP doesn't store well. And that's because ATP is small, so it'll diffuse out of your cell. So you try to have a whole bunch, and it's going to fall right out of that cell because of diffusion. And unfortunately, once it's out of the cell, anybody can use it because all cells use ATP as energy. It's kind of like if you have $20 in quarters and you put them in your pocket and your pocket has a hole, if you start losing the quarters out of your pocket, anybody can use those quarters, right? So they're gone. You just, I lost the money. There's no help with, getting it back because anybody can use that money. Now, if you have $20 and you want to make sure nobody else can spend that $20 but you, what can you do with it?
Put it in your bank.
Put it in your bank. And then how can you spend it if it's in your bank?
With the card?
Yeah, debit card. That debit card is yours and only you can use debit card. Okay? So your muscles, if it has a lot of quarters, it's going to want to deposit that in a way that only the muscle can use. That won't leave. So we're going to transfer a lot of our energy from ATP to creatine phosphate. So we're going to have this whole thing is our muscle cell. We got some ATP floating around. Now, if we've got a lot of ATP, you've got a lot of cash and you don't want to get robbed, you're going to have to go take it to your bank and deposit it so only you can use it. So you're going to have ATP plus creatine gives us ADP, your receipt, plus creatine phosphate. And now only you can use your cash or only you can use your money because it's on your debit card. And if you put your debit card in your pocket, even though you may have a hole, it probably won't fall out because it's bigger than the hole in your pocket. So it's not going to diffuse out. Creatine phosphate is a very big molecule. So once it's made, it stays in the muscle cell. So we'll be able to stockpile lots of creatine phosphate, just like you can stockpile lots of cash in your bank because there's infinite amount of room in there, okay? And it can't get out. Now, if you were to tear your pocket and your debit card fell out, can anybody and everybody use your debit card?
Yeah, no, because
Yeah, it's like in a perfect world, the only people that could use your debit card are those who have the PIN, right? Same thing here. Only cells that can use creatine phosphate are skeletal muscle and cardiac muscle. So if that creatine falls out of your muscle cell, maybe there's a tear or something, all the other body cells are going to ignore it because they can't use it. Only a skeletal muscle or cardiac muscle can. So you might be able to use your parents' debit card because you know their PIN number. So if they leave it at your house and they say, hey, why don't you go get this for dinner? You're like, all right, you're paying. You can use it because you've got the PIN. Okay. Same thing here. The PIN would be the enzyme to break it down. Okay. So to get energy out of creatine phosphate, you would add CPK, creatine phosphatase, giving us creatine and phosphate and energy. Okay, so you would use, pretend I can spell energy. You would use a debit card plus the PIN to get cash. Okay, so when we are at rest and we're not using the money, when we're not using the ATP, we're going to transfer as much as we can into creatine phosphate. That way we don't lose it. And if we do, nobody else can get a hold of it and use it other than us, other than our family, other than our muscle cells. So our muscle stores way more creatine phosphate than ATP whenever we're at rest. That little nugget of information made a lot of drug dealers a lot of money, right? Because if you've ever been to smoothie places, what can you add to your smoothie to make it a healthy smoothie?
Creatine.
You can add creatine. It's powdered protein. It's powdered creatine. Or you can eat a steak, which tastes good. And you feel like you've done something with your life versus a smoothie. Okay, so the theory is if you give your body creatine, that's more creatine phosphate, your muscles can be stronger, they can work out better, and you're going to be super strong and wonderful, right? Listen to the gym rat people. It's on creatine supplements, changed my life. I can bench press. Oh, good job. They say the same thing about the crackheads. Changed my life. Now I can do all the things at once. Now, the unfortunate thing is your body is lazy. Because, well, we like to call it efficient, but efficient just means that you get it done fast enough that you can sit around and do nothing. So you can be lazy, right? If you paid all your kids' bills, would they get a job?
Probably not.
No, if somebody paid all my bills, I would be at home in my jammies, even though it's almost 3 o'clock, still in the jammies, okay? If you pay your bills, if you give your muscles creatine, they're not going to make their own. Okay, they're just going to use what you give them instead of making their own. What happens if you paid all your kids' bills and one day you decide, no, it's time for you to grow up. I'm not paying your bills anymore. What's going to happen to your kids?
They're going to get active.
Yeah, they will. They will be so unhappy. And then what are they going to do after they get over the devastation of not having their bills paid for them?
They start producing their own.
They're going to have to go get a job. They might be on ramen noodles for about a month, but they're going to get a job and start making enough money to pay their bills. That's what happens to your body. You become dependent on creatine supplements. It's just like any other drug. Smoking gives you nicotine, you become dependent on nicotine. You take caffeine, you become dependent on caffeine. You take creatine supplements, you become dependent on creatine supplements. So if you've taken creatine supplements for weeks or months, your body is no longer making its own creatine, you're giving it to it. When you go off the creatine supplements, the biggest complaint, people are like, I'm really tired, I just don't have energy anymore. Yeah, your muscles are tired because they don't have creatine to make creatine phosphate, right? I don't have any cash anymore because my parents aren't paying my bills. Okay, same thing happens when you're doing nicotine. Now you can't stimulate your neurons because you stop the nicotine. Okay, so once you get off, once you go through the withdrawals, your body will start making creatine like it's supposed to, and you'll have your energy back. It may take a week or two. That's lag time, week or two of being tired, being lethargic, not being as strong before you make your own creatine again and you're able to go back to the gym and have the same results. Okay, because when you're on those supplements, that's all you're doing is making yourself dependent, just like making yourself dependent on any other drug that we happen to take. Okay, now that creatine supplements have been on the market for quite a long time, we've done a lot of studies with it. And we now know that if you have too much, you take in too many creatine supplements, you're going to pee out excess because it can be toxic if there's too much of it. And that's going to make your kidneys work harder. So chronic use of creatine supplements can cause dehydration to the point of chronic dehydration. And it can cause kidney problems because it makes your kidneys work harder to get rid of this waste. And it can cause liver issues because your liver has to process the proteins. And if it's having issues with processing proteins, or you're an alcoholic while you're going to the gym, I don't know your judgment, it's your weekend. That's like the worst hangover ever. I feel like crap, I'm drunk. Let's go to the gym. No. But it's one of those, if your liver is already having issues with processing proteins and you throw this extra protein that it has to deal with, that's even more work. So what they have found that prolonged use of creatine is not a benefit to the body. The downside is bigger than the upside. So the constant usage all the time isn't actually good for you. And over time, it can cause kidney issues and liver issues. What they now suggest, if you want to use creatine supplements, you want to just waste your money on something, I'd rather take caffeine because coffee is delicious with lots of chocolate in it, right? Yes, but a lot of chocolate in anything is going to make it taste better. Okay? But anyway, if you're going to use creatine supplements, don't get addicted to it. Take it for a week or two. You get the boost of excess creatine, so you're going to be stronger faster. And then you stop the creatine before you become dependent, before your body stops making its own creatine. So you use it for a week and you got downtime for a week or two. Then you use it for a week and then downtime for a week or two. So you don't get dependent on it. You get the up crest, but you don't get the crash from not making your own. Okay, so it should not be something that you're on all the time. So you don't always need to have the creatine shot in your shake. Maybe once a week, maybe once every couple of weeks, you might get a little bit more benefit from it. But if you're doing it every day, every week, eventually you're going to create a deficit in your own body and you're going to be dependent on that. And you'll have to go through withdrawals just like you would with any other drug that you might be taking. Look at that, I just ruined somebody's gym day. Glycolysis. So glycolysis, again, is the breaking down of glucose. So we do have glucose in our muscles. Depending on the type of muscle, we store different amounts of glucose. So if we need some ATP, we can take glucose and break it down into pyruvic acid. And when we do that, it releases ATP. And that's great. Now, this pyruvic acid, we have options. If we've got some available mitochondria and we've got oxygen, we can take that pyruvic acid and that oxygen into that mitochondria and kick out 34 ATP. And that's why we breathe. So we can utilize all the pyruvic acid and get a whole lot more ATP out of it than just leaving it as it is. If we don't have enough oxygen, we ran out, we're not breathing properly, or bless their heart, muscles are smart but stupid. They get so excited about contracting, they sometimes cut off their own capillaries and they don't get enough blood. Okay? That's why you might have noticed if you try to run too much, you get the stitch in your side.
Mm-hmm.
That's your abs that cut off their own air supply, and now they're having problems. They're like, I'm dying. You're like, stop it. So if you don't have enough oxygen, pyruvic acid is going to sit there and degrade, and it becomes lactic acid. It becomes a complete waste. Just like if you don't eat dinner, it's going to sit at your table and rot.
Mm-hmm.
Okay. Now, lactic acid is what makes your muscles sore the next day. So if you go to the gym and tomorrow you're sore, you probably have some lactic acid buildup because you over-exercise without getting enough oxygen. And it's going to make you tired, going to make you sore. Now, once we have lactic acid, we've got to manage for it. It's a waste. We've got to get rid of it. Like once you have trash in your house, you got to figure out how to get rid of the trash. So what we try to do is kick it out of the cell. There, look, cell membrane. If we can, we're going to send that lactic acid to the liver. And the liver is our body's little mad chemist. It can do a whole lot of stuff. It will do something called the Cori cycle. Fun way to spell it if you want to name your kid Cori. And it's going to take lactic acid and it's going to kick out pyruvic acid or sugar. So it's going to turn that waste into something usable. Similar to if you send your plastic to the recycling company and they make a new plastic bottle out of it instead of throwing it in the trash can. Okay? We want that to happen. If we built the lactic acid, we want to at least get something out of it. Now this is going to happen, it diffuses out. We don't have the ability to kick lactic acid out properly. It has to diffuse. Now it's only going to diffuse if there's more on the inside than the outside. So at some point it stops diffusing. And whatever lactic acid is still here, we still have to clean it up. Okay? That's where we're going to have what we call oxygen debt. If we have lactic acid, it's going to take a lot of oxygen to blast the hell out of that lactic acid and turn it back into pyruvic acid. Okay? Oxygen debt is kind of like credit card debt, right? So if you went and bought a pair of shoes for $50, paid cash, you're done. You don't have to pay anything else. If you bought that $50 pair of shoes with a credit card, is $50 going to clear the note? No, those shoes now cost $62.50. Okay, you have to pay more money to pay off your credit card. If you would have just used oxygen while you were working out, you'd feel fine. No problems the next day. But if you build up lactic acid, it's going to take more oxygen to clean up the mess. Okay, and this is something that we've experienced, right? When we walk up the stairs to come to class or come to lab, by the time we get to the second floor and sit down in class or lab room, we're breathing heavier, right? Mm-hmm. It's okay to admit it. Everybody does it. You're not out of shape. Why? You're walking. You're getting oxygen in. You're processing pyruvic acid. When you start to go up the stairs, you're going to need more ATP to go up those stairs. So you're going to break down sugars more. You're going to produce more pyruvic acid. And if you don't get enough oxygen, you start making lactic acid. So that's going to cause a buildup. So by the time you're at the second floor, you're developing a little bit of an oxygen debt. So by the time you sit down, you've increased your breathing rates because you're trying to get more oxygen to your muscles to alleviate the oxygen debt before it's sore. So everybody's going to be panting by the time they get to the second floor because you're using more energy, more ATP, making more pyruvic acid, needing more oxygen to utilize pyruvic acid or to clean up any mess. Okay, so heavy breathing by the time you get to the second floor is just normal. You're getting rid of that oxygen debt the stairs cost you. So you're going to increase your rate of breathing. Okay. And this is why sometimes it may take days for the muscle soreness to alleviate after exercising. It may take a few days to clear up that oxygen debt if you built it up too high. Just like it may take years of paying off interest on your credit cards if you overspent. Okay. Now the sugar, we can store some to get us through the night. 1.5% of muscle weight is glycogen stored sugar. That little nugget of information made Atkins a very, very rich man before he died of like a heart attack. So his idea, if 1.5% of your muscle mass is sugar and you don't eat sugar, your muscles have to use what they've stored. Magically, you lose 1.5% of your muscle mass. That can be quite a bit of weight depending on your size. Then, of course, you need to replace that sugar because muscles need that sugar there to function properly. So you're going to take any fat and protein that you have lying around. The liver's going to convert it to sugar so you can replace the sugar in your muscles. So if you don't have sugar in your diet, your body will make its own sugar using the liver and the Cori cycle. Now, unfortunately, if your liver is not up to snuff, you're an alcoholic, you don't want to go on the Atkins diet because then your liver's like, really, how much do you hate me? Because it's going to have to work really hard to do that. And it's really messy, makes a lot of waste, which is why you lose a lot of weight in the beginning because a lot of that's just waste material. 1.5%, you got to keep that sugar there so we can do something crazy like live overnight.
So does that fall kind of in the is that kind of what happens when you go on when you fast? Like your body starts burning up that fat and turning it into sugar?
Fasting is just temporary anorexia.
Okay.
Because that's all anorexic is not eating.
Okay.
So if you fast long enough, it will kick your muscle into burning the sugar that it has stored versus the sugar that it can get from the bloodstream. And it's going to create an energy deficit. So it's going to have to bring more energy in when you finally do eat something.
Is it kind of healthy to do that every often to get your liver to produce your body to produce sugar naturally?
You're going to do that anyway.
It's going to do that anyway. Okay.
That's how when you eat bacon, bacon doesn't have carbs. It's going to be able to take that bacony goodness and turn it into a sugar if you need that sugar.
Okay.
And if you have excess sugars, like you're eating Skittles, that's how you can get fat on Skittles, even though Skittles is a fat-free food. If you get too many calories, your liver converts it into fat. So your liver is going to constantly change one to the other depending on what you need it to use it for.
Okay.
So with Atkins, what happens is the protein you eat goes to body repairs, which forces your body to convert fat stores into sugar so your cells don't die because they need sugars. So you break down your fats and you lose weight that.
Okay.
So it's actually a messy, messy job to do. It's kind of like if you buy KFC, your trash your napkins, but if you make fried chicken, there's flour all over your kitchen and there's grease stains and it's a big mess. There's always going to be a big mess if the liver has to make sugar. Better just eat the sugar. So if your ins balance your outs, you'll be okay. Most of us, our ins don't balance our outs. We eat more than we burn.
Okay.
So we store it as fat.
Gotcha.
All right. So at rest, skeletal muscle uses way more or makes way more ATP than it actually needs. So it's going to convert a lot of that into our creatine phosphate. So there's our lovely little math problem over here. When it's time to start contracting, the first thing our muscles are going to do is break down any ATP that we have. So again, this is our cytoplasm. So we're going to break down to ATP to ADP plus P. Here's some. Break it down, ADP plus P. Here's some ADP plus P. And then we're going to start breaking down creatine phosphate. We're looking at about 15 seconds into muscle contraction. So we're moving. We're walking out the door because we think this phosphate, and it's going to go over here and combine with ADP to make ATP. And then we're going to break down that ADP into P, and that P is going to go over here. Make some ATP, and then we're going to break that down in ADP plus P, and that P is going to go over here. There's some ADP, make an ATP, and then we're going to break it down in ADP plus P. 15 seconds, 45 seconds in. Holy crap, we need more ATP. Let's break down sugar. So 45 seconds into your muscle contraction, you're going to tap into your sugar storage to give us a whole lot more ATP. Now, when you're about a minute 15, that's when you start making enough pyruvic acid. You either need to throw it in a mitochondria and get energy, or you're going to start building up lactic acid and oxygen debt. So by the time you get up the stairs, you've increased your breathing because now you're at the point you've got pyruvic acid production, and you got to get rid of it before it becomes lactic. Now, as mentioned, you need CPK.